Alright, everything's looking good, so, yeah. Hello everyone and welcome, to, I guess this is a new series. Yeah, but we're still going to be doing stuff in C and C++, so this will actually, apply to, the OpenGL project, because I feel like we could use this in a lot of ways. So my goal in this kind of project is just to create a very simple, very basic math library. So there will be, I don't know, stuff like vectors, matrices, transformations, operations, and eventually big integers for networking and encryption, stuff like that. So that'll be further down the line. But for today, I just wanted to set the project up and get the vectors going. So yeah. Yeah, so I'm just gonna, I have this repository here. I'm just gonna create a new folder, and I'll call it C Mathematics. And then in here, I will, how do I want to start this? Okay, let's just create our main.c file, actually. Just as a test. Okay. And here I'm going to say include stdio.h and int main printf hello world return 0. And then to run this, I'm going to create batch files, actually, just because it'll be easier just to run those instead of compiling it manually every time in the command line. So I'll actually create a new directory called test. Yeah, I'll call it test, and I'll also just bring it out there. And I will also bring the main.c file into there. And then in test, I'm going to create a run.bat and then debug.bat. In run.bat, I just want to compile it. So make sure that you have the GCC compiler installed. I just made a video on that like 20 minutes ago, I think. So yeah, make sure you got that installed, because you'll need that here. So it's just going to be, or do we need runner? I feel like we could only do it with debug, or we could do with only debug. Yeah, that's fine. So I'll do it with only debug here. So gcc -g main.c. And then, so that'll produce an executable file. So then we'll just say gdb a.exe, and then we can run it through there. So if I wanted to here cd test and then debug, that would compile it, create the thing, and open up the debugger, and then I'll just call run, and then it would run the program. Nice. Alright, so yeah, that's how I wanted to kind of set this up. So this is going to make it easier than having to go into Visual Studio every time and creating a big solution. That'll become more complicated. And this is also going to be just easier to give to someone else. Because if you have the GCC compiler for a Mac or something, you could directly take these files and then just modify the batch file to have it run on the GCC. Or you wouldn't even have to, actually. You would just have to change the extension. I think for Mac or Linux, the extension is different for the batch file. But yeah. So let's just get started, I guess, with the actual math library. So I'm going to create a new header file here called vec.h. And in vec.h, I will include a few things. Include stdr.h and include stdio.h. And I also wanted to create just a general header here, C Mathematics, just to hold a few things like a Boolean per se, because I want to have bool. So in C there's no bool type, so you have to use an unsigned char, but you can actually just make it pretty easily with the type def. So type def unsigned char bool. And then you can just say define true or false as 0 and define true as 1. So not like an invalid comment. This is, oh, this is C++, okay. Or it's Visual Studio Code is interpreting this as C++, but bool is not a type in C. So if I were to go into main.c and include the headers, so include .. slash, oh no. It doesn't like that. Oh, you know what, maybe, you know, I think it's just the interpreter that doesn't like that. So, .. slash C mathematics slash C mathematics.h. Oh, but this is going to be annoying. You know, I'm just going to move the main.c file into just the base directories just to make it easier. Yeah, this series is going to be a lot more informal because I don't have much I'm just going to be winging it mainly. But yeah. But I think I have like a general idea of what I want to do here. So why isn't this letting me? Huh? This interpreter's just, what is this? What is this? Include errors. Please update your include path squiggles or can open source file cmathematics/cmathematics.h. See, I don't understand what that is, or I don't understand why it's giving me that error because you know what? For now, I guess I'm just gonna put them all in the C mathematics file folder. I'll have to figure something out. Okay. There we go. Alright, it's better like this. There we go. Oh, it likes it. No way. That's pretty cool. I gotta get rid of that. And go into CDC mathematics. What are you talking about? It doesn't. Did I misspell mathematics? Oh, I did spell mathematics wrong. Oh my god. Was that the reason why? That might have been the reason why, to be honest. Nope. Don't do that. Okay. Alright, and then I'll just run debug again. Woohoo, it still works. Okay, now for the Boolean, let's say if true, then printf 0, I guess. And then in there, and then also if not false, printf 1. Let's try this one. Hey, it worked. Alright, yeah, so that's just the typedef Boolean. That'll be helpful for some of the functions, per se. Alright, now let's actually get into some math. How about that? We'll start with the structure. or the macros actually. So if, or the includes also for include cmathematics.h. And then in here I want to say if not defined, vec h define vec h, and if. And then we'll have our struct, so struct vec and then I'll say we'll type def actually. Type def struct, and then I'll just call it vec. So this just automatically tells the compiler, okay, you take this entire structure here and recognize it as a vec. So in a vector you have two things really. You have the dimension, so how many elements essentially, and then you have the element array itself. So we'll have unsigned int dim, and then the elements we'll have as a float array, so float pointer elements. We can't have like it as an array pointer itself because we don't know the size of it until we actually construct it, so it wouldn't work. All right, let me actually just check one quick thing here. Aha, perfect. We will also have a value to say vec undefined. So if if an operation is invalid, say if we wanted to take like the dot product or essentially do any kind of operation and the dimensions didn't match, then we would want to return an undefined vector, which we can just use a const. So we'll say extern, so it's available across files, and when we define it, it's actually defined as this one. So extern const vec, and then vec underscore undefined, and colon, and then, or semicolon, and then we'll define this in vec.c, which we can also just create right now. I'll bring this over here. So in vec.c, what I'll have is we'll include vec.h, and then we'll say const vec undefined is equal to, and then for the initialized list we'll have 0 for the dimension, and then null for the pointer. Make sure that's a null and not a null pointer, because C does not have null pointer. Alright. The first function actually we'll have is just an allocation function, just to actually allocate memory to the vector. So vec allocates unsigned int dimension, and then to actually, should I, yeah, I'll go through all the function definition, or I'll go through all the construction definitions right now. And then I will also add documentation once we're done here. So then we'll have a vec construct default vector, where we pass in a dimension, and then we have a value for the default. So this is much like defining it in C really. We're just creating the function definition of the signature here, and then in the source file in vec.c we will actually put the body to it. So this will just create a vector with the same value. Then we'll have vec construct empty vector unsigned int dimension and no default value. This will just construct default vector with a value of 0. Now for the actual constructor, if we wanted to pass in values, we're going to have to do something weird here. So we will say have a function called vec, and it returns vector, or call it new vector. We'll have unsigned int number of arguments, and then we will use the var args, which allows you just to pass in a variable number of arguments. So yeah, so all you got to do there is just press ... and this is included in our stdarg.h file. And then just put a semicolon. Jake, I think your message might have been deleted, because I can't even see it. Maybe it was inappropriate, but if it was, then I don't know. Alright, so to actually do this, you don't want to always have to pass in the number of arguments. That might just become, how do I want to say it? That would be just kind of unfriendly for the user. So to actually do this, we're gonna have to have like a macro function here. All right, now that got through, Jig. What's up? How you doing? Yeah, so we'll have to have a macro here that allows us to actually just pass in just a variable number of arguments, and then we will have to determine the number of arguments in there using the macro. So we'll be using token pasting, which will be pretty cool. So I actually found this on Stack Overflow, so don't, this is not my code here, or I modified it very slightly, but it's pretty much not my code. So yeah, this will just be another function here, and for a macro function, all you gotta do is just say hashtag define, and then we'll have a function here called numargs, and then ... So this will just get the number of arguments in the initializer list, and then we say this returns in parentheses, then size of, then we'll cast something to a float array, and we will cast a 0, comma, and then this syntax is going to be weird, then put 2 hashtags, then underscore va underscore args underscore close curly braces, close one set of parentheses, and then divide by size of float, and then subtract 1. So what is this mess here? Well, what we're doing here in the curly braces is we're just putting a 0 at the beginning. So I'll say 0.0f actually. And then this token here, va args, that actually just gets you, is like the token for the arguments in that you pass into the function, and then we're using this token paster here just to actually pass in the token as well to the to the array, and so then we're kind of contracting them, and then since these are now in an array, we can cast it to a float array. And now that we have a float array, to determine the number of elements, we just have to divide it by the size of a float. And since we had the initial one there, we just have to subtract 1. And this initial value here is for the purpose of allowing us to pass in no arguments at all. So if we just passed in no arguments to this function, it would still have one value, which would be a 0. Then divide by the size of float would be 1, and then subtract 1. Yeah, so it would just work like that. Now to actually have another macro here to construct a vector, we'll say hashtag define vector, pass in the same argument, so ... and then in here we will return new vector. So we'll call the new vector function, and we will pass in the number of arguments. So we'll just call this other macro function here numargs, and we'll pass in the token, so underscore va underscore args underscore, and then we will paste in, once again, the actual argument. So hashtag, hashtag, and then the argument token. So this is pretty cool here. We can define a macro function. I know the syntax is weird, but this allows us to get the number of arguments in a function. And then, yeah. Let me actually try something here. I'm going to put this number of args in the big header here. And then I will also try something with token pasting. So give me 2 seconds to pull something up. Where is it? Preprocessors. Oh, interesting. So what we can do is have a custom type here in this macro, which is kind of cool. Like, let me I don't know, this is from, because I was trying to learn some C. So let me copy and paste this. I'm not going to use it, but I'm just going to copy and paste it just as C. Here, so number of arguments, and we'll pass in a type here. And then the type will be the type for the array, and then the size of type, like that. So we can pass in essentially a custom type, and then in vec.h we will call number of arguments and pass in float, and that might work. All right, let's try this out. So in the main file, we have the mathematics header included, so we can just call. I'll just try and print out the number of arguments. So printf %d for an integer, num args, pass in an integer, and then, or just the type int, then 3, 4, 5, 6, and let's see if this works. Oh my god, it fucking worked. No way. That's sick. Yes, we can pass in a custom type now, which is pretty cool. That's actually awesome. Nice. Yeah, these preprocessors are super nice, are super powerful. And that's just some of the advantages you get with going this low level. Like in Java, Java, they have a built-in variable number of arguments thing, but you don't get this kind of freedom with upper level languages, just to like get all these macros and shit. It's pretty cool. I like it. So now we can actually just use this function anywhere, which is nice. Okay, so that is the macro. So we have construct, allocate, construct default, construct empty, new vector, and then vector. All right, now let's go and actually define these. So we'll start with just allocate. I can actually just copy these functions in here, and you do not need to copy in the preprocessor function because it's already defined, which is nice. Alright, so for allocate, let me just get some space here for the functions. Alright, for allocate, we're going to create a structure. So vec rect, that'll just create or allocate the memory. And then we want to set ret.dim is equal to dim, and then we want to allocate enough memory for the floats. So ret.elements is equal to malloc, so we're allocating memory. then dim times the size of float. So this essentially just tells us, okay, we have a dim number of floats, then multiply that by the size of the float in bytes, and that gives us a number of bytes that we'll need for the elements. And then finally just return ret. So this essentially just gives us a chunk of memory for the actual array itself. Alright, for construct default vector, what we'll say is vec_ret is equal to allocate dim, and then for unsigned int I is equal to 0, I is less than dim, I plus plus, we'll just set all the elements. So ret.elements at I is equal to val, and we can do this because pointers are treated as arrays here. And then return ret. For construct empty vector, like I said, we're just going to call construct default vector with a value of 0. So we just have to say return construct default vector with dim and 0.0f. Now for new vector, we have to create our return. So vec_ret is equal to allocate dim, once again, just to create the space. And now we have to use the variable arguments syntax here. So we're lucky that we get some objects here, or not objects, but just types here. So to actually get the list, we have to say va underscore, or new vector, this should be, let me make num args dim, actually. I'll call that dim. So to get the list, we have to say va underscore list, and then va underscore start. This is a function, pass in list, and then the dimension for the number. Is it not liking that? Oh no, it does. And then we, just to get them, we say for int I is equal to 0, I is less than dim I plus plus. Then ret.elements at I is equal to va underscore arg, list, and double. You can't pass in a float here for some reason. I forget why, but it'll just abort the program if you try and get a float out of a variable argument list. And then we want to free up the memory, so va underscore end list, and then return ret. Okay. Next function we'll have is a print function. Or actually, let's do the copy function first. So let me just create more space here. So this is just simply makes a copy. So vec copy, pass in a pointer, vec v, and we'll pass in a pointer because if we didn't pass in a pointer, or actually, we could just say pass in v and then just return v, because technically that would make a copy of the vector. But you know, we'll do it like this. We can use mem copy. So create the placeholder vec_ret, then mem cpy, reference to ret for the destination, v for the source, and then the size is size of vec, and then return ret. Yeah, I think you could also just, I mean, yeah, we'll try that after. Oh, why did I define it here? That's stupid. And then the next function, and then we'll test it, is the print function, just so we can actually output what we're seeing. So void actually, print, and pass in a vec v. For print, this will be, I mean, you can kind of do it however you want it. I'm just going to print brackets on the side. So we'll say printf, then open brackets, space, and then we'll go through each element. So for unsigned int I is equal to 0, I is less than v.dim, I plus plus. Then we say printf, the format will be %f for the float. then v.elements at I. Then we want to print out a comma. So if I is less than v.dim minus 1, print f, and then have a comma and a space, and otherwise we just print a space because we don't want to have a comma after the last element. And then at the outside of the loop, we'll just print out the closing bracket and a new line. Alright, let's try this out. So we'll go into main.c here, and we will say vec v is equal to vector. Oh, we need to include vec actually. Call the function, and we'll pass in, so you see here, it expects a VA args. This is the macro for the arguments that it will, so the ... expands into VA args, which is kind of cool. So let's pass in here, nice 2, -3, and 1.0. And then we'll print out V. No, I'm just gonna create the actual other. I'm actually gonna create the other batch file, just so I don't have to go into the debug console every time. Oh, and one more thing before you actually run this, since we have another source file, you have to add that to the compile. So the list of files to compile, just add the main.c and then the vec.c, and then. So in the debug, it would be the same. So we have gcc-g and then main.c, and then at the end add vec.c. Alright, now let's run. Nice. Is that right? Yeah, that is right. Fuck yeah. Oh yeah, it worked. Okay, so it doesn't like. Okay, so we need to include string.h or std. Okay, so we need to include those. That's fine. So in vec.c, I guess we just have to include. God, I can't type. std lib.h and include string.h, just for the memory functions. Yeah, that's nice. Let's try using the other functions here. Let's say construct empty vector 5, and then we'll print that out. Prints out 5 zeros, nice. Let's try doing construct default vector with 6.9. No jokes. Hell yeah. And then I guess we can try the copy as well. So vec v2 is equal to copy reference to v1 or v, and then print v2. Nice. Okay, so it works. So let's actually try using the other copy way, where we just pass in not a reference and then, or not a pointer, and then we simply return the argument because it makes a copy when we pass it in. So the new signature will just have a vec in it, no pointer or anything. And then all we gotta say is return v, like so. And then in main.c, I'll just say copy that, and let me see if this works. Oh my god, it worked. Oh right, but C doesn't support overloading, so we have to actually say copy pointer. Yeah, that's another thing you don't get with C. But since we are doing this on C, this will actually allow us to apply this to a lot of things, because think about how many machines actually just run on the lowest level. So we have to write C. We can't even write C++. And in like hospital machines, stuff like that, those run on C. And using such a low level library will allow us to use it there as well. So it has like, we're just reducing the requirements essentially to actually run the program. Nice. But yeah, so that works, which is awesome. Although I think there is, I tried this out, and if you pass in an integer, I believe it might not like some. Yeah, it does. That's. I don't know about that. That one looks. I don't know. But I guess that'll just have to be specified. Okay, don't pass in any integers, so only pass in the float. God damn it. Okay, so that's mainly the allocation and basic methods. Now let's get into actually some of the operations. So there are going to be a buttload of them. So I'll make the definition. Alright, let me see them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Interesting. Alright, so there are 20 functions now. This is going to be fun. I mean, but let's just walk through them one by one, and then. But this, then I think I might just wrap it up after this. I mean, we've only been live for just over half an hour, but regardless, this is going to be. Some of it will be interesting, but it's mainly going to be self-explanatory. So the first function will be just bool compare, or we'll call it bool equals. Pass in a vec v1 and vec v2. Now going back to vec.c, we'll paste in the function signature. And then in here, all we want to say is if v1.dim is equal to v2.dim, then we can actually compare them. And we'll just compare each element. So for unsigned int I is equal to 0, I is less than v1.dim, I plus plus. Then we'll say if v1.elements at I does not equal v2.elements at I, return false. Then outside of the loop, we'll say return true. And then outside of the if statement, we'll say return false because the dimensions do not match. Nice. Should we test it? Yeah, let's test it. Doesn't like this. Argument type of bool. Oh, I'll just say v1 here. There we go. Wait, is it still doesn't like it? What do you mean? I don't know. What? Incompatible type for argument 1 of print. Equals returns a bool. That's a character. No? Oh, print F. That's why. Okay. Yeah, okay. %C. Or %D, actually. I'll So we print out the integer value. There we go. 1, that's not, what? It was working just a second before. Uh-oh. Oh, wait, that's right, because I have to call new vector, or wait, no, that the reason why was because that that thing. Yes, sorry. So construct default vector actually. Now this should work. There we go. So it doesn't equal. And if we add 5, they should both be equal. Perfect. Alright, next function will be scalar multiplication. So return vec scalar multiplication, pass in a vec v and a float k, and then we also have a second way just to pass in multiply a pointer, so we don't have to return a copy. So we'll just have a return type void, scalar multiplication, vec pointer v and float k. Or wait, scalar multiplication by, once again, because it does not support overloading. I will insert comments after. Alright, for the first one, we have to create a return variable. So vec ret is equal to allocate v.dim, then at the end return ret, and then for unsigned int I is equal to 0, I is less than ret.dim, I++, ret.elements at I is equal to v.elements at I times k. So just get the element in the original and multiply it by k. Now for the one with the pointer, it's simpler. You just have to do in the loop unsigned int I is equal to 0, I is less than v.dim, I++, v.elements at I times equals k, since we're modifying the pointer itself. Then we'll have scalar division. So this is actually pretty much the same, except we're just going to switch the operation. So scalar division and scalar division by. And I'm actually just going to copy the function definitions too, because I'm too lazy. And then we'll have ret.elements at I is equal to v.elements at I divided by k, and then v.elements at I divided by equals k. Like so. Yeah. This Animal Crossing music, it's very nice for the background. I mean, that's pretty, I don't know, that's then what a hot take, yeah. I don't know, it's nice just to have on. It's not like energetic or anything, it's just there, which makes it special, I guess. Alright, back from my sidetrack. Well, I do that way too much. Now we're gonna have the vector operations. So that was like Vector-scalar. Now we'll have vector. So this is element-wise operations. So we'll have the 4 addition, subtraction. I don't know. Addition, subtraction, multiplication, and division. Element-wise, though, not dot products yet. All right. So we'll have a vec add, vec v1 and vec v2, and then similarly to the other ones, we're going to have vec add, or bool, return type bool, add 2, and we'll pass in a vec v1 pointer and vec v2. And then I'm actually just going to copy these for the subtraction too. So subtract, and then subtract from. For add, we have to check for the dimension match once again, because you can't add two vectors that are in different dimensions. Like, let's say we had a vector in 3 dimensions and then one in 2 dimensions. You just simply couldn't add them because the elements do not match up. So we're going to say here if v1.dim does not equal v2.dim. Now, since we return a vec, we can't return false, but what we can say is return the const that we had up here. So vec undefined, which is the reason why is a specific reason why I added that in there. So return vec undefined. Otherwise, though, we'll allocate a vector. So vec red is equal to allocate v1.dim. And then for unsigned int I is equal to 0, I is less than red.dim, blah, 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 blah. God, that is annoying. Then we'll just say ret.elements at I is equal to v1.elements at I plus v2.elements at I. Why did I choose this stream? This is so boring, my lord. And then return ret. And then similarly to the scalar multiplication by and scalar division by, for the that add to, wait, what did I just do? Oh wait, I did that wrong. Okay. Oh, I'll just do add 2 actually. So for add 2, if the dimensions do not match, we will return false, because it returns a Boolean. And then otherwise, we'll just add the elements. So instead of allocating a new vector, we're going to delete that. And then we'll still say for unsigned int I from 0 to v1.dim. We'll say v1.elements at I plus equals v2.elements at I. And then we return true at the end. Alright, so this is going to be the same format for subtract from. Just make sure that you put the right operation in. Okay, but the principle here is that you're just iterating through each element and adding, subtracting, or doing whatever. Alright, so for the next functions, we're going to have multiply, multiply by, divide, divide by. So you know what, I'm actually going to talk about something else while I just do this, because I feel like it's pretty self-explanatory. It's actually the same exact format. So what do we want to talk about? What do I want to talk about? I heard there was something about in the Smash community today. What's up, Venkatesh? Oh, did I ask your name? I feel like I've asked your name before. Is it Venkatesh? I don't know. Yeah, I don't know. Apparently, yeah, Nintendo. Yeah, you know what it was? Nintendo had their big dick energy once again and just stripped a tournament, an online Melee tournament, because Melee didn't have like the built-in online functioning, so they just so they were using a mod, and Nintendo doesn't like when they use mods, so like with Project M or something, Nintendo straight up banned that shit from hacked Wii's. So yeah, they just straight up canceled the tournament because I think people were making money from it. So that's not too good, I don't think, for the Melee community, and I guess the Smash community as a whole. But you know what? Maybe Nintendo will have a change of heart. But you know what? I don't know what Nintendo, because I want to say that they're better than other companies with this shit, but I'm not entirely sure, to be honest, because they've done this before, and they haven't like re-gifted or allowed Project M or anything. They've just left us with their freaking shitty online platform. But did I do that? Yeah. But who knows? Maybe they'll have a change of heart in the times in this crisis, and who knows? Maybe we'll be able to see some hot Melee tournaments all over the net. Yeah, so I guess I kind of finished that there. Yeah, it's just the multiply was just the same format. If the dimensions didn't match, return the undefined vector, otherwise allocate a vector and set each element to the multiplication of the elements in the two vectors. And then for the pointer, it's just make sure the elements match, and then just multiply the element directly since we're using a pointer. I pronounced it right. Can I make Gerstner waves? I don't know what that is, so let me... I have no clue what this is. Trochiodal. This is, I'm assuming it has something to do with water. In OpenGL from scratch. Looks cool. Yeah, I got a lot that I want to do in OpenGL. I'm gonna be 100% honest with you. Like, I want to do some more lighting stuff because I gotta finish up the shadows. But then I also want to incorporate like noise or Perlin noise into the shaders, and then I guess we could honestly look at this at some point. That'd be honestly, yeah, this looks cool. Fluid dynamics is an exact solution of the Euler equations for periodic surface gravity waves. In computer graphics, right? Multi-component, multi-directional extension of the Lagrangian description of the free surface motion. Yeah, this, I don't know, what is this? What is this? God damn it. Oh no. The free surface, so I mean, this looks kind of like some noise stuff, I'd say. Actually, it does, yeah. Where you modify each component. You have the unit normal vector. I know what that is. I know what the normal vector is. I also know what this means. These are the derivatives of what is this? The S? I don't know what S is. Looks cool though. Yeah, maybe at some point I'll get to this. I will definitely mark this down though. Okay, now to the other vector operations. There's a few of them. So we're going to have the dot product. Now the dot product is essentially the element-wise multiplication, but then just the summing of the elements in the vector. So we multiply each element together, and then we just add them together. So we add the products together. This is used to determine orthogonality or perpendicularity. So if two vectors are perpendicular, and then this is also able to determine the parallel component shared between two vectors. We've looked at this with lighting, that sort of thing. So we can just do it now. Float dot vec v1 and vec v2. And then in here, we'll just define it. We'll just have a placeholder for float ret is equal to 0.0 float. Then just go through. Well, first we actually have to determine if the dimensions are the same. So if v1.dim is equal to v2.dim, we'll say for unsigned int I is equal to 0, I is less than v1.dim, I plus plus. Ret plus equals v1.elements at I times v2.elements at I. So we're just taking the product of the two elements, the two corresponding elements rather, and they're just adding it to the sum. And then at the end, we just want to return ret. So if the elements do not match, we will just return 0. And then for orthogonality, we'll just have a method to return bool orthogonal vec v1 and vec v2 here. And then we'll just have the same signature. And then we'll have a ternary operator. I'll have, so return v1.dim is equal to v2.dim if they are. We will return the dot product of v1 and v2 is equal to 0.0 float, otherwise return false. So yeah, this just determines, okay, are these two vectors perpendicular? And that's just determined if the dot product is 0. So if you sum up all the products and you get a 0, that will determine that the vectors are in essence perpendicular, and this works in all dimensions. So yeah, this kind of library here that we have is pretty I want to say this is going to be good if we want to generalize something. So this could be used for graphics, and I might actually just integrate this into my OpenGL engine. But this can also just be used for any sort of data analysis. So if you have a vector of data, which you will often have in data analysis and statistics and linear algebra, in the hospital setting, you'll have tons of data. You can represent it with vectors. And I mean, this is more linear algebra stuff, but if you wanted to determine if two vectors were orthogonal, that might mean that they have no commonalities. So this is more, well, so like if we had like a survey of data actually, and we took the dot product, and like each vector represented one person, and then we took the dot product of the two vectors and they were orthogonal, then that would mean that they are uncommon, or there's nothing that's parallel between them, which is a more practical application of the dot product, which is kind of cool. So yeah, I'm not going to teach you linear algebra, but that's just one of the many things that you can do. Okay, and then we're going to have the next thing will be a cross product. So vec cross, vec v1 and vec v2. Turns out the cross product can only work in 3 dimensions. Well, it can work in 0, 1, 3, and 7 technically, but it's only used in 3 dimensions. So we have to check that first. So if v1.dim does not equal 3 or v2.dim does not equal 3, return vec undefined. And what the cross product is it just essentially returns a vector that is perpendicular to both v1 and v2. And it is found through the determinant of a matrix. Once again, if you don't know what that is, don't worry about it, but you just get the formula from it. You don't have to know how to do the determinant now. But we will actually define an algorithm to, when we do matrices, we'll actually look at splicing matrices to find the determinant, which will be cool. So yeah. So for the cross product, we get the formula from the determinant. So vec_ret is equal to allocate. And we can just pass in a 3 here because we know that's the dimension. It doesn't like, okay. And then we can set the elements individually. So ret.elements at 0. So this is going to be a shit show. So let me actually just pull up the... It's this formula right here. You guys can't see that. This, here we go, this is better. So yeah, essentially you get this formula from the determinant of this matrix, which is composed of the unit vectors, then the first vector, and then the second vector. So it just reduces to this formula. So I'm just going to write it out now. This is going to be, oh god. Let's say, okay, so ret.elements at 0 is equal to, in parentheses, v1.elements at 1 times v2.elements at 2, close parentheses, then minus v1.elements at 2. Here, let me just make this there right now. Here we go. v1.elements at 2 times v2.elements at 1. Then ret.elements at 1 is equal to -1 times, then in parentheses, open up another set of parentheses because we're essentially going to take something that looks like this and then just multiply it by -1. So in the first set of parentheses, we're going to say v1.elements at 0 times v2.elements at 2, close the first set of parentheses, then minus, open up another set of parentheses, v1.elements at 2 times v2.elements at 0. You might recognize some patterns here. If you do, nice. And once again, the patterns exist because it's simply the determinant of that matrix there. So I'm not going to prove it right now. It's just it would be off topic, but this is the formula. You kind of just have to trust it. There's a whole proof for it, but yeah. And then ret.elements at 2 is equal to v1.elements at 0 times v2.elements at 1 minus v1.elements at 1 times v2.elements at 0. Like so. And this returns the cross product. Alright, now some other, just a few more functions here. We're going to have the magnitude squared first, and you'll see why we're doing the squared magnitude first. Or we'll just define float magnitude, pass in a vec v, and then another float magnitude squared vec v. So this just essentially allows us, or the formula for the magnitude is just the sum, is the square root of the sum of the squares of the components. So you take all the components, you square them separately, and then you take the square root of that. So that's why we want to have the magnitude squared, because we might not want to square root it in some cases. There are a bunch of cases where you don't want to. So for this, we'll actually need to include cmath in the source file, because we do need the square root function. we'll say cmath.h, I believe is, or no, it's just cmath. We'll start just by pasting the functions here. So for the magnitude, we'll say return the square root of the magnitude squared of v. So once again, that just comes from this function, or the formula here. And then for magnitude squared, what we're going to say is we're going to have a float ret is equal to 0.0. Then for unsigned int I is equal to 0, I is less than v.dim I plus plus. Then ret plus equals v.elements at I times v.elements at I, which is just the power. And then return ret. So once again, it's sometimes more efficient just to compare the square, like in the distance formula. Or actually, no, not the distance formula. We encountered this when we were doing 2D collisions with in the Pong project. Oops. There we go. Alright, let me find the code, or just the, here we go. Where is it? Yeah, I gotta sort or look through all this. Yeah, so the collision here, when you're determining the collision between a square or a rectangle and a circle, you can use the square distance, and it does the same thing, because if the square distance is, if the square distance is greater than another squared value, then if x squared is greater than y squared, then x will be greater than y. So that's how. So you don't always have to take the square root, which can be costly in many cases. Let me just refill my water real quick. My voice is getting too raspy. Okay. Last, or I'm not going to say last, but close to last, we're going to have two functions here that will allow us to normalize a vector. So normalizing a vector essentially just allows us to take a vector and make its magnitude 1. So I'm just... We've seen this a lot in the graphics. So it's kind of like the unit vector essentially. So we just take the vector and divide each component by its magnitude. So it essentially just allows us to compare vectors of magnitude 1, which is helpful with the dot product. So like when we were looking at lighting, this is important. So yeah. So we'll say vec normalized vec v. So this will just return the normalized version of the vector. And then void normalize, we'll take a vector pointer and just normalize it. So we'll copy these in. So for the top one, we'll have a vec ret is equal to allocate v.dim, and this returns a vector. Like this, the normalize operation returns another vector. It doesn't return a float. It returns another vector. Then we get the magnitude, so float mag is equal to magnitude of v. I'll try something after this where we might not have to actually call the square root function, which will be interesting, but for now I'm just gonna leave it like that. Then for unsigned int I is equal to 0, I is less than ret.dim I plus plus. Then ret.elements at I divided by equals mag. So we're just taking each element and we're dividing it by the magnitude. Then for normalize, we're going to get the magnitude is equal to magnitude, and then we have to dereference v. So just put an asterisk v, and then for the same for loop, then v.elements at I divided by equals mag. Okay. Nice. I just thought of one more thing, one more function I wanted to do, which would be the element-wise power. So if we wanted to raise each element to the power of something, so I can just put that up over here, I guess. So vec pow or power. What do I want to call this? I'll just say power. So I'll say raise, or no, power. Pass in vec v and float k, and then void power of vec pointer v and float k. This is getting messy and long. Jeez. For the power function, you allocate a vector of size v.dim, then go through each element and say ret.elements at I is equal to the power, which is in the cmath, cmath header, and we'll say pow f, and pass in v.elements at I and k for the power. And then for power of, it's similar to the scalar multiplication by, where we just take each element and say v.elements at I is equal to pow f v.elements at I and k. Alright, so now let's go ahead and test all of this stuff. There's so many fights. Jesus Christ, there's so many. But you know what, that's the fun. Alright, so let's take let's construct two new vectors here. We'll test the scalar operations first. So vec v1 is equal to vector, pass in 1.0 float, 2.0 float, negative 3.0 float. Print v1, then vec v2 is equal to scalar multiplication, pass in a v1 and 3.0 float, then print v2, and then we'll also say scalar multiplication by reference to v1 and 3.0 float, and then print v1, and we should get the same result. So if I run this now, we get 5. Oh, did I even oh, okay. So I guess it's cmath.h, right? Yeah, that makes sense. Didn't like that. No, there's another error. There's no such thing as cmath.h. Is that so? Oh, it's math.h. Alright, yeah, that makes more sense. This isn't C++, it's C, so there's a math header. Oh, great. Oh, did I not change the names or something? Oh my god, I didn't change the names. That's stupid. Oh wait, no. oh yeah, I didn't change the names for the division functions. So there were just two, scalar multiplication and scalar multiplication by. So now let's run it. Alright, so 1, 2, 3 is the original, then multiply by 3, 3, 6, 9, and then have the pointer, so nice. Alright, that works. Now let's go the other way. Let's do scalar division. And scalar division by. Same answer, good. Alright. Now let's do the addition, the element-wise operations. Or let's do the power first. So v2 is equal to power, and we'll do the power 3, and then power of for the reference. 1, 8, negative 27, 1, 8. Alright, that one looks good. Give me 1 second. Give me a hot second, sorry. Alright, sorry boys, I just had to, I just went and put a gun to my neighbor's face and told him to shut up. That's exactly what I did. And then I also went to the bathroom. Okay, oh my god, they didn't take the message. Fuck. Okay, let's, sorry, let me just, give me 1 more second. Or, you know what, I'm good now, sorry. Getting too paranoid about this. Alright, let's test with the addition, subtraction, multiplication, and that sort of stuff. So vec v2 is equal to a vector this time, we'll say 2.0, 3.0, negative 4.0. Then we'll say vec v3 is equal to add v1 and v2, we'll print out v3, and then we'll also try the pointer, so add to a reference to v1 and v2, and print v1. So we should get the first one, the second one, and then two of the same sums. Looks good, nice. Now let's do subtract. And then subtract from. Let me actually just make sure this math is right. 2 and 3, yeah, good. 1 minus 2, negative 1, negative 1, 1, nice. Now let's do the multiply. And multiply by. Run this again. So 1 times 2 is 2 and 2. 2 times 3 is 6, 6. Negative 3, negative 4 is 12 and 12. Good. What else do we have here? Divide. Oh, no. 1 divided by 2 is 0.5. 2 divided by 3 is 0.66667. And negative 3 divided by negative 4 is the 0.75. Okay. Now for the dot product. Let's have some fun here. Or, let's do the normalized vector first. I will get an example just to make sure this is all right. Alright, want to give me an example here? I don't know what that number is. I need, I'll grab my calculator. So we'll actually just print out the magnitude as well here. So print f, %f for the float, and we'll pass in the magnitude of v1, and then we'll also pass in the magnitude squared, just to make sure that works as well. Okay, so 1 squared plus 2 squared plus 3 squared is 14. So I got a 14 as that, which is good. Did I not return something here? Oh, I didn't return the normalized vector. Nice. Nice, attaboy. Oh, that is, what? What the fuck? Alright, well, let me just make sure the magnitude works. Square root of 14, 3.74, good. The normalized, oh, ret.elements at I, that's why, okay. Because ret is 0, okay, that makes more sense. Ret.elements at I is equal to v.elements at I divided by mag. So make sure that you're dividing in the normalized function, make sure you are dividing the vectors, the input vectors elements by magnitude, rather than the empty vector. Now if I run it, we get the same result. Let me just make sure this works. 1 divided by that, 0.267, 2 divided by root 14, 0.53, and then 3 divided by root 14, 0.801, negative 0.801, nice. And then for the other ones, we get the dot, or let me actually try the second thing, or the other way I want to do this. So if we have, if the normalized is equal to the element divided by magnitude, then it will be equal to the element squared divided by the magnitude squared. The reason why I want to do this is because it's much easier, since square root is calculated with a Taylor series, which is a loop essentially. I don't want to do the loop, so I'll just say v.elements at I times v.elements at I, and then I'll replace magnitude. Let me just move this over here, and I'll place magnitude with the magnitude squared, and just call magnitude squared there, like so, and do the same thing down here. And then in the normalized function, we'll say v.elements at I times v.elements at I divided by mag squared. And if I run it again, we get Oh, because there's no... there's something not right. Did I do something wrong? Oh, and then I need to take the square root of that. So you know what? Never mind. That's wrong. Okay. Yeah. You know what? That was. We're gonna have to call the square root either way. So it's better to call it once with the O. Yeah. So that was just my thing, and I could be intelligent, but no. So yeah, just keep it as is, because we're gonna have to call the square root at some point. Nice. Okay. Let's try the other functions. So the dot product, cross product, and orthogonal. So we'll take vector v1 as that. Vec v2 is equal to the vector 1 or 2.0 float, 3.0 float, negative 5.0 float. Print v2. Then vec v3 is equal to the dot product of v1 and v2, and we'll print out v3. Or, sorry, it's a float. So we printf the float and just print out v3, like so. Run this and I will verify this with my calculator. Or 2 times 1 plus 6 is 8, plus 15 is 23. Good. Now let's get a set of 2 orthogonal vectors. Come on, give me 2 vectors that are perpendicular. Come on, come on. Give me this. Just give me an example of 2 perpendicular vectors, please. No, no, no. You know, I'll just use this. Wait. There was a good one somewhere. Alright, this one. Oh my god. 4, alright. 4, 1, 2. Like that. And then the second vector has to be 4a plus 2c is equal to 0. Where b can equal 0. So we'll say, so 2a is equal to negative c. So 2a is equal to negative c. If a is equal to, or c is equal to negative 2a. So if a is 1.0 float, b is 0, and then c is negative 2.0 float. And then we want to say printf the character value, orthogonal v1 and v2, and this should return true. That is it. Oh, that's the character value for 1, I think. Print out the integer value. Aha, nice. Yeah, so that's the dot product. Now for the cross product, last test of the day. I want to get another example here. Here we go. 2, negative 3, 1. And then negative 2, 1, 1. Negative 4, negative 4, negative 4. That was what? Did I input something? I'm getting okay, so I guess I input the something wrong. Cross product. Red dot elements at 0. Alright, let's take out the debugger here. So this is just using GDB as the debugger. So I'll say break vec.c colon 342. Okay. So that just allows us to break at in this file at line 342. So if I run, we'll have a breakpoint here. So I'll print out v1.elements at 0. So it was 2, negative 3, 1. Print v1.elements at 1. 2, negative 3. I think the elements are okay. Is the math right? 1, 2, 2, 1. Alright, what it didn't, so it was the last element that we weren't getting right. v1.elements at 0 times v2 at 1 minus v1 at 1 times v2 at 0. Let me step over. Or, no, yeah. So print ret.elements at 0. Negative 4, print ret.elements at 1. Print ret.elements at 2. Alright, so that's like a 0 right now. But when I move, let me try. Let me do this. Print v1.elements at 0 times v2.elements at 1, 2, and print v1.elements at 1 times v2.elements at 0. 6. 2 minus 6 is negative 4. But I should be getting... Oh wait, they just did this wrong. That's actually right. Yeah, this is wrong. Because it's a minus... Because the negative 2 times the negative 3... Let me flex my knowledge right here. The negative 2 times the negative 3 is a positive 6. So 2 minus 6 is negative 4. This should be negative 4, negative 4, negative 4. What the fuck? Never go to math.info.com. What? Look at this bullshit. Get out of here. Get out of here. What is this bullshit? What is this? Can I leave a comment somewhere? Oh, 2007. Yeesh. You know, I'm joking. Go hear this. Look, this actually looks like they have a lot of shit here, which is cool. But it's wrong. That's wrong. And there's no related topics to this at all. This is never, cross product is never ever used ever. But yeah, so our shit works. Attaboy. So yeah, I will add comments now actually, but that's gonna be I'm not gonna do that on stream obviously because that would just be pointless. But yeah, so that's the beginning of our library. Next video thinking of doing matrices. Matrices are a much larger topic, so I don't think we'll be able to get through that in one video. So that'll likely be creating the matrices and then splicing them, which will like getting certain elements of an array, or getting certain columns and certain rows of an array, which will be useful for the determinant. So yeah. Yeah. This was useful, I think. Yep. So if you want to follow along, the code will be committed in, once I finish the comments, to the repository somewhere. Here's the repository. Yeah, I'll have the code in here in like 20 minutes maybe. But yeah, so I hope you guys enjoyed, especially the Animal Crossing music here. It was a fat hour and a half plus of just jamming out to some Animal Crossing music. So yeah, hope you guys enjoyed, and I will see you maybe tomorrow or Saturday for some Minecraft. So yep, I'll see you then. Have a good one.